Hi, my name is Chris, and this is my DSP project on recovering a blurred signal. This is from problem 5.65 on page 366 of our textbook. So the problem says, in many practical situations, we are faced with the problem of recovering a signal that has been blurred by a convolution process. We can model this blurring process as a linear filtering operation, as depicted in figure 5, 5.65-1. The blurring response is also shown in 565-2. In problem 5.65, we are considering ways to recover Xn from Yn, the blurred signal. One approach to recovering Xn from Yn is to use an inverse filter, such as the one shown in the figure. H inverse is simply 1 over h of e to the j omega. H e to the j omega is the Fourier transform of Hn, and if you remember from figure 2, Hn is nothing but a series of delta functions between 0 and n minus 1. For the impulse response Hn, shown in figure 2, discuss the practical problems involved in implementing the inverse filtering approach. So why is this problematic? From my experience from building an inverse filter for image processing, the first huge problem that you run into with this kind of filter is, what if the transfer function has zero frequencies? You cannot divide by zero or frequencies close to zero because this would cause your image to blow up, or in this case, your signal. The output Yn may carry some noise, so the noise will be amplified if you divide by frequencies close to zero. This will cause your recovered image to be nothing but amplified noise. Now, the practical problem involved in implementing the inverse for this particular impulse response is that the transfer function becomes an infinite sum when inverted. This cannot be used as a real-time filter. So let's take a look at that. So from figure 5.65-2, we have h of n is equal to 1 for n 0 to m minus 1 and 0 otherwise. So if you look in table 2.3, there is a Fourier transform of that. And if you use Euler's formula, you can break down the sine components into e to the j omega m divided by 2 minus e to the minus j omega n divided by 2 over 2j. And so the 2j's cancel, and on the right side you have e to the minus j omega m minus 1 divided by 2, because remember that we are plugging in m minus 1 for m from table 2.3. This simplifies to h e to the j omega is equal to 1 minus e to the minus j omega m divided by 1 minus e to the minus j omega. And so the inverse of that, you just simply flip it. The discrete time signal hi of n becomes the summation of delta n minus km minus delta n minus km minus 1 for k between 0 and infinity. Part B says, because of the difficulties involved in inverse filtering, the following approach is suggested for recovering Xn from Yn. The blurred signal Yn is processed by the system shown in figure 5.653, which produces an output Wn from which we can extract an improved replica of Xn. The impulse responses H1n and H2n are shown in figure 5.65-4. Explain in detail the working of this system. In particular, state precisely the conditions under which we can recover Xn exactly from Wn. So we have two filters, H1n and H2n, shown in figure 5.65-4. H1n is the summation of delta n minus km for k0 to q, and H2n is delta n minus 1. So part B asks us to explain this system. So this is a windowed version of Hn inverse. H1n convolved with H2n is equal to H inverse n times Bn, where Bn is 1 for n between 0 and Qm and 0 otherwise. If you remember in chapter 2 on page 61, we talked about the windowing theorem. So from figure 5.65-3, we can say that Xn convolved with Hn convolved with H inverse n times Bn is equal to Wn. If Xn is shorter than Qn points, it can be recovered by looking at Wn between 0 and Qm minus 1. Part C says, let us now attempt to generalize this approach to arbitrary finite length blurring impulse responses Hn. Assume only that Hn is equal to 0 for n less than 0 or n greater than or equal to m. Further, assume that H1n is the same as in figure 5.65-4. What condition must Hz satisfy to implement H2z as a causal system? H inverse of z is equal to 1 over Hz, which is also equal to H1z times H2z because convolution is multiplication in the z domain. H1n is equal to the summation of delta n minus km for k between 0 and q, which is from figure 5.65-4. The z transform of this is 1 minus z raised to the minus qm divided by 1 minus z raised to the minus m. We can figure out what h2z is from these two statements. It is equal to 1 divided by hz times 1 minus z to the minus m divided by 1 minus z to the minus qm. Basically, h2z is 1 over hz times h1z inverted. So h2z has m zeros and qm poles. H2 is causal because there's no pole at infinity. Hz poles and zeros, p and z, are related to h2z by z plus m has to be less than or equal to p plus qm. The zeros of hz plus the zeros of h2 must be less than or equal to the poles of hz plus the poles of h2z. This concludes my project on recovering a blurred signal with digital filters.